Digital images are ultimately just grids of raw pixel values. Early networks processed these grids by flattening them into a single, one-dimensional line of data. This immediately destroys the spatial relationships between pixels. Convolutional neural networks exist specifically to solve this problem and preserve that spatial geometry. Here on the left, we have a simple two-dimensional input matrix. On the right, the complex, multi-layered 3D tensor architecture the network builds from it. A precise series of localized mathematical operations directly connects this simple starting grid to that highly complex output. To understand how these networks function, we have to drop the black box analogy. We can derive the entire architecture from first principles, beginning with a single matrix operation. Mastering this deterministic, element-wise math is an absolute requirement for any practitioner working with visual data. A convolutional layer starts with two primary components, the input image matrix and a smaller matrix called a filter or kernel. The kernel is a highly specific feature detector. Its mathematical values are tuned to identify specific patterns in the data, like a vertical edge. To perform a convolution, we take our 3x3 filter and overlap it onto the top left corner of the 6x6 image matrix. The operation itself is simple element-wise multiplication. We multiply every overlapping element in the image matrix by its corresponding element in the kernel, and sum those 9 resulting numbers together. That calculation collapses those 9 values into a single feature value, -5, placing it into a new output matrix. The kernel then shifts across the grid, repeating this process. It slides systematically over the entire input matrix to calculate the remaining cells. Because a 3x3 kernel cannot extend past the edges of the input grid without running out of data, our original 6x6 image shrinks down into a 4x4 output. The data located at the absolute edges of the input is chronically underutilized. If we want to build networks with dozens of layers, we cannot let the data shrink with every operation. We need an algebraic mechanism to force our output dimension to perfectly match our input dimension, which we'll call n. This introduces the concept of padding, or P. Padding is the programmatic addition of symmetrical, empty cells, usually zeros, around the outer border of the original matrix. To find out exactly how many layers of padding we need, we set up a core dimensionality formula. N plus 2p minus the filter size f plus 1 equals n. We isolate the padding variable p. Moving the terms gives us 2p equals f minus 1, leaving us with exactly p equals f minus 1 divided by 2. If we plug in our filter size of 3, the math dictates a padding there exactly 1. By wrapping the original image in a single cell border, the output matrix will perfectly maintain the original 6x6 dimensions. Padding provides a deterministic lever to protect the spatial integrity of an image as it passes through deep layers of the network. While padding preserves dimensions, there are times we want to intentionally compress them to distill out higher-level features. Here we can look at stride, represented by the variable s. Stride defines the specific step size the kernel takes as it traverses the data. If we set the stride to 2, the kernel shifts by 2 units per calculation, deliberately skipping over intermediate columns and rows. By forcing the kernel to take larger steps, a stride greater than 1 aggressively downsamples the spatial resolution of the output map. We combine these into a single unified equation, the floor of n plus 2p minus f divided by s plus 1. This master equation governs every single spatial transformation in a convolutional network. So far, we've looked at 2D grids, but real images are actually 3D tensors, containing multiple distinct color channels. Our variables must expand to account for height, width, and channels. Moving to 3 dimensions introduces an uncompromising mechanical rule. The filter must have the exact same depth or number of channels as the input volume it is scanning. Here we see a true 3D convolution. The input is a 6x6x3 volume, which requires a matching 3x3x3 kernel to properly overlap the channels. The operation calculates all 27 overlapping values simultaneously. They are multiplied and summed together, mathematically collapsing the 3-dimensional depth back down into a single value in a flat 2D output. A single kernel acts as a single feature detector. To extract the complexity of a real image, we need to locate dozens of different features simultaneously. We accomplish this by applying multiple distinct filters, what we will call K, to the exact same input volume. Each independent filter runs its own convolution and produces its own independent 2D feature map. These separate feature maps are then stacked together face-to-face, forming a brand new 3D activation volume. The spatial height and width of this new tensor are strictly governed by our master formula. Its depth, however, is dictated entirely by how many separate filters we choose to apply. Stepping back from these micro operations, we can see how they govern the macro architecture of a complete network. This schematic diagrams a deep convolutional workflow across 3 major tensor blocks. In the first transition, the input volume drops from 39 by 39 down to 37 by 37. The nodes specify the hyperparameters: filter size 3, stride 1, 0 padding, and 10 separate filters. Applying our derived master formula, 39 minus 3 over a stride of 1 plus 1 gives us exactly 37. The math perfectly maps the architectural change. Moving to the second transition, the spatial dimensions aggressively compress from 37 down to 17. The critical variable here is the stride of 2. 37 minus 5 for the filter size, divided by that stride of 2, plus 1, dictates the 17 by 17 output. Simultaneously, the depth it spans from 10 channels to 20, strictly because 20 independent filters were applied in this layer. A convolutional neural network is a chain of rigid dimensional transformations. It systematically distills raw pixel data into dense, highly compressed feature representations. There is no magic in deep learning. Underneath the hood, computer vision is built entirely on predictable, deterministic matrix algebra.